So I think I spoke with Kyle on Friday, and he was going to come to this Casper Standup to present an idea that he had um, for the cost model. But I think we don't have Vlad yet. Oh, is Vlad's on?
Yeah, I'm here.
Okay, all right. Well, I guess we can go ahead and get going, and
I'm
hopefully.
trying to convince Georgios to join.
Okay.
Looks like Kyle just sent out a link to a wiki page, which presumably has something related to what he wants to talk about.
Okay, cool.
Quickly, while we're waiting, Doug Rushkoff has asked about why the people with the most money are going to control our chain, and I couldn't give him a simple answer. Is there a real quick, simple answer?
Yeah, it's not necessarily the people with the most money.
Okay.
And the protocol is really in charge. Like they don't get to do anything like produce invalid blocks or change the IO model or there's a whole host of things. The only thing that the stakeholders get to do is determine the order of blocks. All they do is form consensus on a data structure predefined by the protocol. The role is actually rather minor.
Well, he's consented to have a Zoom session with us at some point, so maybe the end of next month.
Cool.
Where I guess he can get a better answer if people participate.
Or he can come to one of these and ask.
Yeah, he's pretty busy. We are setting up some Zooms, but the schedule is tight.
Understood.
I will mention that.
Okay. All right. Do we want to get rocking?
I guess so.
Okay.
Oh, is Georgios here? You said,
yeah, he's here. Yeah.
Okay. Cool.
Oh. Who wants to go first?
I'm about to get into an elevator, so I shouldn't go first.
Okay. Well, I mean, my update is pretty simple this week. I mean, because I was extremely busy with the developer conference. But I think Vlad and I had a good discussion about instead of using sets of messages as protocol states, using program states of programs as protocol states, and what that entails. Like, there's a big difference because program states don't necessarily form a category, at least not with the small step semantics. You only get a category if you have big step semantics. So that's one difference in using that approach. And Vlad sent me over a definition of the requirements for protocol states, which I thought was a good beginning. I'm looking forward to thinking through that. So that's my update. Nice and short.
Cool. Yeah. I wouldn't mind giving a quick conversation about the proof within programs.
Okay.
So the kind of the idea is that we have the same requirement that we need to maintain a protocol state in common, if and only if there are, or at least if there are less than some number of equivocating faults.
Mm-hmm.
We can define equivocations in roughly the same way.
Yes.
Normal. Common future states become common future program states. And that's just fine. The concern is that only programs that have some kind of commutative operation, so that receiving messages in different orders will lead to the same state, will kind of work out. But
Yeah.
But that's not so bad. So the one kind of thought is that, like, oh, maybe the way that we think about whether they could reach the same state might be connecting two validators together and letting them run communicating for forever, or like potentially forever, until maybe they get to the same state. Because that will, at least that's analogous to what we're doing in a sense.
Yeah. I mean, you do have structural equivalence on the states, and if you use an asynchronous calculus, then the release of messages, then every channel is effectively an unbounded queue, and the messages can be reordered because they're all in parallel composition and they're all equivalent. Hello?
Sorry, I just did the elevator.
Okay.
But the different terms, I mean, you might have messages that can only be observed after other messages are observed. And so it's not quite, they're not quite independent of each other, because like messages include messages and justifications.
True. Yeah, that's a good point. Yeah.
Cool. Who wants to go next?
Kyle's on now, so Kyle could go.
Okay.
I should probably go at the end of the updates, because we're going to probably discuss this for a while.
Okay. Does anyone else have any updates they want to give?
Sure. I guess I have a bunch.
Okay.
One Greg already covered. Another one is, I sat down with Nate, Michael Birch, and Kent, and we worked on sharding for a few hours on one of the nights this week, and came up with a new sharding protocol with that satisfies the kind of weakest definition of cross-shard atomicity, that works with queues and message passing.
Okay.
And when there's a queue, there's like an obligation to when you see on another shard a queue that is full of messages incoming to your shard, there's an obligation to empty it and execute those transactions for some amount of the block. And so basically shards have like the choice of like never communicating or emptying these queues. And so the main kind of way to think about it is the shards they're raising some kind of graph structure, and when there's an edge connecting them, there's queues going from one shard to the other and vice versa. And they basically monitor each other's queues. And they pass messages back and forth, basically, if they ever have new messages with justifications that include updated views of each other's queues. And those queues have messages in them. So
Okay.
it's like a sharding solution that guarantees the atomicity of a transaction kind of eventually. And the cool thing about it that wasn't featured in my sharding solution that my first sharding solution was one of these eventual atomicity solutions, and then I came up with this like immediate upfront atomicity solution. And this one's even weaker than my initial one. It turns out, because the one I was doing previously was finalizing a whole transaction at once, whereas this will finalize a little bit of a transaction at a time until it finalizes the whole thing. If ever, but certainly it can't finalize anything inconsistent with the stuff that's already finalized. So it ends up sidestepping some of the synchronization problems that I used to have with my cross-shard finality when I was trying to finalize transactions as a whole, because transactions could have like a little piece late in the transaction that is, after some other transaction that isn't finalized, which has a little piece later that's after some other transaction that isn't finalized. And so if you try to finalize the transactions on a wholesale basis, you end up having to finalize big chunks of them. But now instead, what I get to do is finalize like a little piece of transactions at a time, starting from like the most, like the kind of the unfinalized piece in the most distant past. Well, there might be a bunch of them, but one of those. And so the sharding solution is a big update. Is Nate here?
I didn't see him.
Okay, well, I guess I'll give updates for our work together also.
Okay.
We've been working on a description of the protocol states. Specifically, we kind of realized that like any proposition about the protocol states themselves would also benefit from the safety proof if they can never be invariant in all future states. And so we're looking at the shape of that consensus protocol, basically of like some consensus protocols that decide on properties of protocol states. So specifically, we're looking at this protocol that for every protocol state decides whether or not it's always going to have a common feature with it, or if it never will. So once two states are called lost, if they don't have a common feature, and I don't have a great name yet for when they do have a common feature, but you can have two states that have a common feature for all possible future states. For example, a state and any past state that it has.
Sure.
And so there's a decision for every node, or for every protocol state as to for every protocol. So for every protocol state execution, every complete protocol execution would make a decision for every protocol state whether or not it is going to be lost forever or not lost forever, meaning forever not lost. And so there's like somehow like you think of it naively as a binary consensus protocol on all these infinite protocol states. And you can show that every protocol message from a node that hasn't already been seen to be Byzantine does lead to some set of lost messages. Some set of lost protocol states. And so in some sense, this protocol is like, and we kind of believe the protocol is like, in some sense, maybe maximally deciding. And we kind of kept looking at this thing, and basically, any state that has more than T Byzantine faults in the union with the current state is lost forever. The ones that don't have that property aren't lost, and the ones that are in the protocol's immediate past are always going to be, not immediate past, possible past. So there's when you think about a consensus protocol or any protocol's current state, it doesn't actually encode the trace of all its past states. So we have to have this notion of possible past. And then for us, that will contain like any possible order with respect to having received these messages. And so there's lots of paths for every protocol state. So we call it the past cone. So anything in the past cone is going to be safe forever, in the sense that safely having a common future state with the current state, even as the state evolves. And the only kind of exception to this is the states that include new messages from Byzantine validators. Those ones also, so including new messages from validators who are already seen to be Byzantine does nothing, and therefore is always freely common future state. Kind of like, we can each see any number of messages inconsequentially from nodes who have already observed to be Byzantine. And so the nodes, so the messages that we've decided on end up being, all the possible pasts, all the possible pasts plus all futures that correspond to only receiving messages from those who have already received to be Byzantine. And then all states that already have some number of Byzantine calls are the ones that are lost, and all the other ones are bivalent. This is like a current hypothesis that we can split it up in this way. So ones that show too many faults are we've decided 0 on. The ones that are in our past cone or in our past cone modulo additional messages from nodes who are already observed to be Byzantine are just 1, and then the ones that aren't in either of those sets are bivalent. And then we kind of reason that this actually describes perfectly well the tunnel that the consensus protocol is making through the consensus protocol space, and that somehow this consensus protocol, where the estimator is kind of like the identity, all it decides on is like which path through the consensus protocol space that we kind of went down. So it's kind of an interesting, it's an interesting case of a consensus protocol where instead of using an estimator that is like something we normally care about, we just imagined, oh, what if we made propositions about the protocol states themselves? And because that would also benefit from the safety proof, which is that like, oh, different safe properties are consistent for any nodes that have a common future state. So that's some of our work, and we also did some more on like definitions and
Vlad, is what you just mentioned the automatic finalization versus
it absolutely is. It absolutely was. I was assuming automatic finality for that, all that, and I mean with the kind of vanilla protocol spec, it is all automatic finality. Manual finality is like some next level ish,
So
it
when you
involves like a argument in the estimator about what the protocol's already finalized.
Yeah, so when you mentioned automatic finality on like Thursday, like, is this what you were referencing, or was there like
no? And all the CBC protocols, unless you have an estimator that takes in the finalized stuff that you don't want it to return, are going to have automatic finality.
Cool. Yeah, I see.
Yeah. So what this exploration was is kind of like of a minimal or maximally deciding consensus protocol, depending on how you think about it. And so all it has is just the very core of the CBC stuff, the stuff that makes sure that you have a common feature as long as there's less than 2 faults, or not more than 2 faults rather. Yeah, so I guess that's my update, new sharding solution and some analysis of and looking at the nature of the decisions in the CBC consensus protocols, where the decisions are understood as decisions to go through particular protocol states and to lose particular protocol states, as opposed to being decisions about some estimator or the value that some estimator returns. Yeah, so that's I guess that's pretty much all.
Cool. That's a juicy update. Who goes next?
I'll go next. So just two quick updates, hopefully. The first one is that I pushed the Turan Oracle. And the second one is that, let me just share this screen. So I typed up, I guess, like a pro-con table for what we discussed over the dev conference, specifically about the tree and lattice models. And I just wanted to make sure that I got it right. Yeah, the on the tree model, basically, we can do atomic transactions speculatively, and then we don't have to do receipt tracking. And the higher shards, so to speak, can reject merge blocks. And you don't have this, I guess, exponential sets that you need to validate if you were interested in one of them, theoretically. And then finally, there's, if you're in the tree model, then it can take a while to finalize compared to the lattice model, because you have to essentially get your blocks merged into the top, through a chain, so to speak. Or you have to get it into a state such that none of them can change their fork choice in the future. I just wanted to especially check on this point because I'm not sure about this one. Vlad, do you have, I guess, input on this?
Well, I mean, it just sounds like you're applying the definition of finality, so I don't know. It sounds like you're just giving the definition of finality.
So
as opposed to a way that this is actually achieved.
Well, so I'm saying that you don't need to merge blocks to the top shard in order to have it finalized. Like you can satisfy this definition without merging blocks to the top shard. Does that make sense?
I mean, it depends on the model, I guess. Like in my atomicity first kind of tree model, as opposed to the eventual one, you can't do that. With the eventual one, with message passing in queues, we can.
So yeah, I'm talking about your sort of tree, like eager atomicity. I don't know what to say, model.
Yeah.
But why not? I guess.
Because they can't really be finalized as long as their parents can orphan their blocks, and so they only can finalize the last thing that was merged into the root ultimately.
The parents retain the ability to override them. That's why.
Except for in as far as they've already committed to a particular state.
If the parents have already committed to something, they can't override themselves, but they can override decisions.
Yeah, exactly.
Past that point.
Yeah. I was wondering
we can make the protocol a little more complex to avoid that to some extent by having the child post commitments in the parent, which the parent can't ignore. but I'm not doing that right now. It's like it doesn't really seem like a huge win for the complexity.
So yeah, I understand that part, but I was thinking that, if you get all your sort of child chart validators to commit to a certain block, then they can't, like, how is the
They
parent
can't by themselves revert those blocks, but the parent can.
by
Unless
just,
they've
I
unless
see.
they've already merged with the child at a later block.
Well, so is it not possible to add a rule such that a parent shard cannot add something or like mine a merge block with something that conflicts with all children right now?
That is already a rule.
Ooh, wait. But isn't that?
Oh no. So it's only the children block that the parent block knows about. It can't be expected to follow and have received any blocks that are in the justification of the block that it's making, right?
Well, I guess I'm confused because it seems like,
So nothing's forcing it to see these blocks, right? It might never see any of them, and that's why it chooses the next one in line as opposed to the one like way down the chain. Obviously, if the validator who's making that block has already committed to seeing those blocks from that child chart, then it's another story because we can get them to execute the fork choice rule on the tip of that child. But we don't want to force all the validators and the parent to keep track of all of the blocks from the child, and so we don't do that.
I see. Okay, fair. Then that's great. Yeah. So I'll have to remove this second point, but yeah. But otherwise, that should be it for me. Yep.
Cool. You should add the new sharding solution in there too. The
Yeah,
message
will do.
passing on. Yeah, it would be really that table could be a valuable resource, I think.
All right. Is that mine? It's my turn.
Yeah.
Okay.
Unless Georgios wants to give an update.
Oh, yeah, that's right.
Did you want to go last?
Okay, just a brief update, something that to touch on something we did with Vlad last week. It had to do with like proving that a specific type of proving properties of a distance metric for a way of understanding the topology between like different future and past cones. Vlad, do you remember what I'm talking about?
Yeah. So we defined this metric, which is okay. So if a node, should I define it, or do you want to define that metric?
Go for it.
All right. So we define this metric on protocol state space, where basically if two protocol states, if one of them is in the future code of the other, then the metric is the number of states required to get to it, like the number of minimal state transitions required to get to it. And then if they have a common future, but they're not in each other's future cones, then the metric is the minimum number of steps required to get them to a common future state. So you count steps on both sides, right? So essentially, they were talking about the metric in the first, give it in the first stage for when they are in their future in the common, when they are in each other's cones for their unions. So like if we allow like d sigma prime to be the distance metric from sigma and sigma prime, where sigma prime is in the future of sigma, then the distance for two states that have a common future is d of sigma 1 comma sigma 1 union sigma 2 plus d of sigma 2 comma sigma 1 union sigma 2. So it's like the sum of their distances from their union. And if they don't share a common feature, then the distance metric is unbounded.
Isn't the case, so aren't there only the three values that this can take then? 1, 2, or infinity? Because you can compose.
No, because we're talking about the number of minimal state transitions.
Right, but you can compose state transitions, right? So
yeah, but only some of them are called minimal, right? And if you compose them, all of a sudden they're not minimal. They're like minimal only if they can't be decomposed. It's like a
So like receiving one message is minimal, receiving two messages is not.
Exactly. Yeah.
Yeah.
Cool.
And so you could think of it. You could think of it as the total number of messages that two states need to receive so that they are at the common state. And unbounded if they can't ever reach a common state by receiving messages. Anyways, Georgios, you want to talk about the metric?
I mean, so the main thing is that we prove that like this metric actually exists. It's well defined. So we view it as a tool about actually working onto like embedding these actual like possible histories on a topology that's defined via this metric, and then using this type of like topology to actually like argue about valid executions of Casper, right?
Do you want to talk
now
about
the
proof? Oh, sorry.
I mean, okay, in principle, I could talk about the proof, but I don't think it's very useful. I don't have, I don't have the proof in front of me. Something I can share, and it's probably like a bit complicated. But what's the large scale idea? I mean, okay, the large scale, the main idea is to try to prove that all of the properties, that this definition is consistent with all of the properties of a proper metric. And the property that's actually a bit tricky to actually formally prove is the triangle inequality. And that's the thing that was so like nailed on Wednesday. So there is a specific it actually works, and we can so like share. We can definitely share the details, but I think it might be more useful to do something else on the next half an hour or so.
Yeah, and so could you tell us a little more about the idea of like trying to use the metric space to give an embedding or something like that in some other kind of space?
Well, okay. So in some sense, I think we're trying to visualize the correct executions of like of Casper, and in sense also like what should be reachable by a valid execution of the protocol. So there are two different ways in terms of like trying to think about like valid executions. Like one of them is to try to think of them a bit abstractly via somehow just invariant properties of the protocol. The other one is to think of it like in a more constructive way by saying that, okay, I describe this specific like structure, and I give some specific like metric properties on the paths that I consider valid. And now every sort of like path that sort of like satisfies these metric properties is a valid path. So both two such descriptions, in principle could be equivalent, but like mathematically or constructively, they can give you like different tools to argue about like possible paths. And this idea of metric embeddings can give us like new tools, like new mathematical tools to argue about valid such executions. I think we're actually trying to. So the next thing that we're trying to do is like we're trying to visualize the such valid paths for different somehow like properties or different like protocols. But I think we but so far we haven't really made any progress on trying to capture a non-trivial protocol. Try to, in some sense, to visualize a non-trivial protocol, like using this idea of metric of this underlying like metric distance.
Cool. Any more updates before Kyle? Take it away, Kyle.
All right. So one of the things that has bugged me for a long time about rolling is I didn't have a good model about a transaction, right? Like, how do you define a transaction? Because there's things that we'd like. So I'm going to give you like a working example, but you can imagine a slightly larger example. Like, we have a sell contract, and we want to make sure that like that the interactions leave it in valid states. So I was listening to Mike's talk. He was talking about the necessity operator, and I realized that we could use something like pre and post conditions to. I thought about post conditions as a way to specify rolling transactions. The problem with that is that the post state you reach depends on what's currently in the currently around, and that isn't a very workable definition. Excuse me.
Unless you have a pre state also.
Yeah, so that's the point of this proposal. So like, if you look right here at the cell contract, and I have some strawman syntax that we can bicker about later. I don't think most people are going to be able to type the black triangle. I just used copy pasted it from Unicode, because that ideally that's what it would be, because it's easy to read but it's hard to type. So the idea is that so this receive would form a transaction boundary, in that in order to execute, it needs to be in parallel with the following addition or terms that match the following patterns. So the equals here means reference. So whatever method is, there has to be a right on it that matches this pattern, and whatever state is, there has to be a right on it of val, which is arbitrary. And then the body has to reduce to a right to state, and in this case, it had better be val, and a right to the return channel, and it had better be val. So the nice thing is, when you if you evaluate it in parallel with just that, then you can run it to quiescence, and you can verify that what is produced is the post state. We can use this to handle things like transactions for out of flow errors. So if you don't get to this, if you run out of flow, right, like, well, we know where the transaction boundary is, and this also has the nice property of that you have a good idea of what computation you're paying for, because like, it can only reduce so far in the presence of what you said it should have. So like, if we look at the modified contract, this one starts to do something non-trivial, right? Get, right, like, we could just evaluate it with only the satisfying rights present, and that would work. But modify, we don't want to do that. We actually want to evaluate it in the presence of more. So in this case, we have modify. It's a method call. It takes a channel F, and we grab the state lock. And so we read the value off the state and lock it at the same time, basically. So we need a write to method. We need a write to state, and we need something listening on F. And it needs to reduce to, and this actually enforces that whatever's listening on F is a pure function, which is actually kind of what we want. We don't want it modifying anything else. And then it reduces to just the state. We could have a different version of modify that took in modify F and a return channel, in which case it would reduce to something like here, a write to state and a write to the return channel. So this has a bunch of nice properties in terms of a transaction model. Number one, this is some syntax that would be useful even for Rolang as a general purpose language. Modulo a few tweaks, which I'll explain in a minute. But like you would want to be able to, like if you were going to write general purpose Rolang, you might very well want to write these pre and post conditions and have them checked at runtime. And we can try and, if you have a post condition, the preconditions you kind of have to have at runtime, and I'll tell you why. But you can, you might be able to prove that that given the precondition, it will evaluate to the post condition, and then you can elide the check if you can. So like this might be like this body here.
You mean you might be able to prove without executing? You mean?
Yeah, you might be able to prove. Yeah, like at a compilation step that there's no need to check the post state because it will always resolve to that. On the blockchain, we probably need to because of things like out of flow errors. But in a general purpose programming language, you might be able to prove the post state always follows. So this allows you to do things like this allows you to post a deployment along with its prerequisites, right? Like what you're willing to pay for it to evaluate in parallel with, and then run it to quiescence. And this allows you to have very nice control about how much you're paying for, right? Rather than posting a Rolang term and like hoping for the best.
Yeah, so it actually looks a little bit, it's kind of halfway between pre and post and rely guarantee.
Yeah, so one of the things that's interesting is that these are linear preconditions, and they're not like classical logic linear or preconditions. So the preconditions must either be consumed or present in the post conditions. So like this method right and this state right get eaten. Like if I put an additional precondition on like something else, it would fail unless I also put it in the post condition. So they're linear in the sense that they get consumed and they must be preserved if they're not consumed. They also kind of act like import statements, which is kind of a funny thing. But basically, you import the amount of code you're willing to reduce in parallel with. And we will probably want syntax sugar for, like there's a pattern here already over. So the method right has a pattern, and we suggested like some syntax on the read that says, yeah, put this as a precondition in the type so that you don't have to write it twice.
Yeah.
So yeah, both of these, are kind of implied by the read. Although in terms of like what you're willing to pay for. If you don't want to pay, if you want to post a contract, you can post it without those preconditions, and then you don't pay for its evaluation. Even if somebody has preloaded that contract name with rights that would satisfy the patterns, you're not, since you're not importing it, you're not paying to evaluate it in that context.
And is your proposal then that this is optional? So, I mean, you don't have to write pre and post conditions.
Yeah. So if you don't write preconditions, we have a couple of options. One is to default the preconditions to just the rights.
Sure.
Another is to default them to true, right?
Right.
Where like so, or true in yours case, but like we would just use underscore. If your precondition is underscore, we import everything and we evaluate the heck out of it.
Yeah, I see.
So if you're willing to pay for whatever's there, you can just put your precondition as underscore, and you better put your post condition as underscore too, because if you don't know what you're getting, you don't know what you're going to result in if you're importing everything.
Yeah. So I think that the main thing is just making sure that this plays well with anticipated language features, right? So in particular, you know, if someone has a behavioral type and they had the pre and post conditions, then there's a consistency issue.
Although can you say in a behavioral type, like if you place it in this context, it reduces to the following?
Yeah, I mean, that's the rely guarantee types. That's the whole idea of rely guarantee. That's why I was saying this is kind of halfway between a pre and post condition and rely guarantee.
So yeah, the thing that it differentiates this from rely guarantee types is that we reduce all the way to quiescence and then we check. So if you produce a type that produce a state that it must go through but isn't fully reduced, we won't stop at that state.
Yeah.
So you mean if I put a non-quiescent post condition on the right-hand side, that would be a compile time error because post conditions necessarily have to be quiescent?
Yeah, that's what I'm thinking. Although if it's a must, right? Like then like we could check it at each reduction, because if it's a must and we don't reach that state, then you've written a state. You know, then if there's if there's a reduction path that avoids that state, then it's not a must. Is that, you can correct me if I'm wrong, Greg, but if must means that it's basically a choke point, that there has to be a state that goes through there.
Yeah. There's a bit. I'm sorry, I'm thinking about this other problem. So I think for bounded recursion, so basically this would check if you have unbounded recursion because you can't quiesce.
Yeah, you couldn't quiesce in the presence of unbounded recursion. Well, the nice thing is that if you run out of gas without quiescing, or even if you run out of gas without quiescing, well, you imported the things that you requested, and you gave us some gas and we ran it, and so now we have a proof that it didn't reach the state you requested, and so we can roll it all back.
Sure.
Right. Like the nice thing is that in the presence of if you don't reach the post state, it's like the read never occurred. But you can post the proof that you didn't reach the post state and collect the transaction fees. So you might even get a gas refund, right? Like we ran it, or like, so if you called modify, but there was nothing listening on F, right? Or your F didn't reach this this final, like it had some other side effect, then like we can refund the gas, roll back the or refund part of the gas, the part that wasn't used in the transaction. We can roll, but we still publish the fact that it didn't reach the post condition and roll it back. And this is nice for things where you want safety guarantees, like wallets. You want certain invariants to hold.
Yeah, I think this is a nice proposal. I don't, as long as it's optional and it doesn't, you know, I mean, there's additional consistency checking between, you know, something like this versus the behavioral type. So we have to, going forward, we have to decide, you know, like the consistency check could be too hard to prove, right? So
Well,
then you
can
have
we could we use a behavioral, but just are behavioral types strictly more powerful than this?
yes, they will be.
Okay, so I mean, it's possible that that maybe like you can have a behavioral type or pre and post conditions, but not both. And we use the behavioral type to derive transaction boundaries.
Yeah.
The nice thing about this is that like there's a nice operational model in that, like, we import the things you requested, we evaluate it until we stop, and then we collect payment at that time, and then we push the results back in, you know, down a level into either the next waiting transaction, or if it's a deployment, we push them down into the block state, or into the you know, the R-chain state, and then there might be other things in the tuple space with payment waiting whose preconditions are now satisfied, but like there's a nice boundary about who's paying for what. There's a nice operational model there.
Yeah, I understand. I mean, the thing that I like about this is what we've said up to now is that the transaction boundary is default comprehension, right? But that is, a comma event is not the same kind of transaction or not necessarily the same kind of transaction as a wallet, as the, you know, sort of wallet or balance updating transaction, which is what I think a lot of people view. So what you're proposing is a generalized transaction boundary.
Yeah. So you specify what needs to be present and how far it needs to reduce. And so you can put a 4, like, yeah, so there's a 4 in here, and this 4 right here doesn't have a type, but this whole thing has to reduce to here. So, or we don't, or we roll it back.
Yeah. I mean,
and F has a 4 that we imported.
Yeah. It's a very nice feature. I like the feature a lot. Any comments from anyone else?
I mean, it seems like a natural kind of thing, but I don't really understand the details enough to really comment.
So about the behavioral type, I'd have to think about that. Maybe I'll talk with Mike about like whether those conflict today. But I just wanted to get people's take on initial take. It seems pretty positive.
Yeah. I mean, I think it's a pretty cool feature. I can't. All I'm just trying to do is to see if there's any collisions with any other language design directions that we're trying to go in. and I can't see any collisions right now, but we should be, think about it with an eye to that.
Yeah, so it might be that in Venus we supersede these with behavioral types.
For example, that's another possibility. Yeah. Cool.
Yeah, an interesting idea. I don't necessarily exactly see how to leverage it, but I guess as Greg says, maybe the number one priority is to make sure that it doesn't have any collisions with other specifications. But I guess
so the leverage I think is clear, right? What Kyle is arguing is that with this we can go after a particular payment model, right? So the user puts in the pre and post condition, or a form
pre and
of
post conditions.
Yeah, exactly. And then we can check, and if we don't hit the post condition, then we get to roll this back.
Have to pay.
Yeah, and then the nice thing, one of the things is we could even allow the user to use unforgeable names to specify the pre and post conditions.
Right.
But just not the term they're deploying. So if you're paying, if you're updating somebody's balance, right, like you can specify that your balance is 40 less and theirs is 40 more as a post condition, right? Like if it doesn't reach that state, like that's bad, and we don't want to include that.
I mean, do we get in a place where the evaluation of the pre and post condition is computationally expensive?
At the moment, they're just spatial types. So like these ones we have to match anyway. So yes, it is possible that finding them could be expensive, but at the moment they're spatial types, so it's not awful. It's like any other pattern match that a read or write could do.
No, we could get into a situation of trying to match against a par, right? And if the par has lots of components, then it's exponential. But most people won't write those.
Yeah, it's exponential in but like we're pulling things out of the tuple space basically. So the existing state is reads and writes. So we have to find a matching write.
So if you don't have to match against a bunch of no, but it's still possible to have a big par.
Yeah, you could have a par inside of a body.
Yeah, exactly.
Right, right here.
Yeah, so that. Yeah, so okay.
But we could just right, like that's part of the computation you're paying for is that and we could record how much it costs to do that because we're planning on doing that anyway. Like if you do, right, if you write to some key that's hard to, well, no, if you have a read that's with a pattern that's really hard to match, I mean that's just basically the same.
Yeah.
Because right, like F here, right? That's what we're looking for. That's basically what we're doing is we're going to the channel and we're looking through the fours to see if there's a receive that matches the pattern. It's not any harder than the other matching that we're already doing.
Yeah, understood. Yeah. So I'm actually the model here is like you get what you pay for, right? So if you if you put in some giant some really really ridiculously hard thing to match against. Oh no, I guess it's the other way. It might work the other way around. Hang on a second. So it could be that the tuple space is in a, like you've just got one par, but the tuple space is set up so it would be really really hard to calculate that match. So so that is a bit of a tricky one.
So it's not really that bad. Like the complexity is complexity is what's on this key, or like what's on this particular key, and then the pattern that you specified. Right, like so this part we actually just checked for quality there, and then this body. So if there are a lot of things listening here, and you have a very complex body, but you can control this part, right? Right, like the user is who's calling modify supplies F, and so they're the ones controlling how many, they can supply an F where there's exactly one thing listening. And
yeah, I hear what you're saying. I just think about this. We've got stand up now, so we got to jump over to the other one.
Okay.
All right. See you over there. Thanks, guys. It was a really good. I think there's a lot of good updates here.
Okay. Bye.
Yeah, thanks everyone. Bye-bye.